Okay. Oh, okay. So this example that I have on the screen now, is that the one you're asking me about? Okay, let me erase some things, and I will go over it. Oh, I just selected it. While I'm doing this, I do want to mention that I am going to post your next exam today. It'll be due not this Friday, but next Friday. To give you a little over a week to do it, so I can give. But it's going to be just like what your homework is that's due today. So you'll see that it's very. I mean, the data will be different, but what I'm asking you to do will be very, very similar to what you were just doing in your homework. At least that should give me some room to work here. If I can find out where I am. There I am. So, here we go. All right. So here is our PDF, and it's asking you to determine a sufficient statistic based on all sorts of different knowledge. Now, in the first video that I did about sufficient statistics, the definition involves that conditional probability eliminating the theta, the parameter that you're trying to find the statistic for. However, you have to know what the statistic is before you can determine whether or not it's sufficient. So that's a little bit harder of an idea, because I have to know what I'm looking for in order to look for it, which is weird. So the other ways that we talk about trying to figure out if a statistic is sufficient or not comes about from being able to write your PDF in a certain form. So one of those was factorization theorem, and the other is the exponential form idea. So the exponential form is the one that looks like let's go back to drawing. E to that k of x. Make sure, of course I erased all that. I want to make sure I have the same letters that I had before. Do I have that anywhere? There it is. So we have that k of x, p of theta. That was what I was looking for, was the letters. The p of theta, the s of x, and the q of theta. That's all up in the exponent. So that's how we're trying to rewrite our PDF, where we're trying to find a sufficient statistic for the theta. So for the gamma distribution that we have here, we've got the 1 over gamma of alpha, theta to the alpha, x to the alpha minus 1, e to the minus x over theta. So our goal, if we're trying to write it in exponential form, our goal is to write everything as e to a power. So for this for the last part here, this already is e to the power. So I don't need to mess with that e to the minus x over theta piece at all, because I already have it as e to a power. So the rest of it, we just do our trick of writing it as e to the natural log. So just taking this whole piece and putting it inside the natural log here. And then combining our things together so that we can see if we can rewrite it as that exponential form, if we can split it apart, how the form says we need to be able to split it apart. So First thing I have is we would have, let's see, I would have a negative natural log of gamma of alpha, and then a minus, I mean, I'm going to write it this way anyway, minus a natural log of theta to the alpha. And then we've got a plus alpha minus 1 natural log of x there. And then we can add that to our other exponent. Then we have another minus x over theta piece. I think I've got all my stuff using the properties of logs appropriately there. Okay, the reason why I don't really need to, I did split them apart in this case. You don't really need to split them apart because, I'll leave it that way. I don't really need to split them apart because I only need to worry about things getting split apart if I've got an x in them. Because this is, in that first part of the exponential form here, the important part of this is that where the part that where the x's and the thetas are mixed together, I need to be able to split apart as a product. One just has x in it and the other just has theta in it. I don't have the thetas and the x's linked together where I can't split them apart as factors. Like, for example, if you had an x to a theta, I wouldn't be able to break that apart easily because it's not a multiplication. All right, so, yeah, okay. So, this part here, we're trying to do this for theta. So we're assuming first that alpha is just some number. Ooh, my wind picked up a little bit outside. Sorry about that. Well, the first part, we're assuming that alpha is just some number, and it's the theta that we're trying to find a statistic for. So this part, let's see if I can get my red again here. This part here is the function of theta with no x's in it because alpha is just a constant. So this part is your q of theta. This part is your function of x with no thetas in it. So this part is the s of x. So those two pieces are split apart like they're supposed to be. One has to be a function of theta with no x's in it. One has to be a function of x with no thetas in it. The last piece is that product piece that we need to split apart. So we can see that this piece is minus 1 over theta times an x. So the minus 1 over theta part will be the p of theta, and the x part will be your k of x. So being able to write it in this form tells us that we're in where you have exponential form here, so that we can conclude that our y equals the sum of x of I is sufficient for theta. Does that make a little bit more sense? Uh-oh, my speaker's off. Why is my speaker off? Can we hear me? Yes, my headphones got unplugged, apparently. Try that again. Sorry about that. Does that make more sense? Did that help? Yeah. Yes, that's correct. So, it'll always be the sum of whatever the function is that you split it apart. So, going the other way, if we were trying to find a sufficient statistic for the alpha rather than the theta, notice this piece then would be your p of alpha k of x here. If I was trying to find if I were worrying about the alpha rather than the theta, that would be the part where it's factored apart. So then your sufficient statistic there would be your sum of your log of x of I, because it's the log of x that I see as my function. Yeah, that's exactly right. Yep. That's exactly right. Good. Other questions? All right. Well, let's talk about some new stuff then. We will come back to the sufficient statistic idea. Again, the reason why we care about the sufficiency aspect of things is so that we know that we've taken every bit of information that we can from the sample that we have to give us information about the parameter we're trying to estimate. That's the whole point of this exercise, is to try to come up with as good of information as we can based on the sample we're given. To that end, not only do we want as much information as we can possibly get, we would also like to know how good is the information. So that's what this lecture is going to start talking about, is the idea of the quality of estimates. So we've talked a little bit about the idea of bias in an estimator. So let's start with that again. So remember that we say, as a definition, we say that an estimator, we'll call it theta hat, for theta, is unbiased if, when we do the expected value of the theta hat, we get theta. We've seen examples of both biased estimators and unbiased estimators. For example, when we do the expected value of our x bar, when we do the sample mean, the expected value of that is our population mean. So x bar is an unbiased estimator for the population mean. Oops, I forgot the word estimator in there. Okay, so we have an unbiased estimator for the mean here with our sample mean. We've also seen that our sample variance, the expected value of that is the sigma squared. So again, our S squared is an unbiased estimator for sigma squared. Oops. Now we've seen other things that are biased as well. So, for example, when you do, instead of doing the 1 over n minus 1, when you do the 1 over n for your, when you try to compute your sample variance, when you do the 1 over n, your expected value for v here, pardon me, isn't sigma squared anymore. It was what? Well, we have a 1 over n minus 1 out in front for this one to make it unbiased. The expected value for this is what? It's n minus 1 over n times sigma squared. And this is why we use s squared rather than this v. This is why we always divide by the n minus 1, because we want to get that unbiased estimator for the variance. So when we do the sample variance, that's why we divide by the n minus 1 instead of the n, because of this factor that we have out in front. So this is a biased estimator. And we've seen other ones as well, but the idea of bias has to do with, on average, what should your statistic be coming out to? And it's unbiased if, on average, it should be coming out to the true value of the population parameter. So we actually have a measure of the bias. So when you do the bias of an estimator, the bias of the estimator is going to be the expected value of that estimator minus the actual parameter value. So that's how we get a measure for bias. So obviously for the sample mean and the sample variance, the bias is 0. If you wanted to know the bias of this V, so if we want the bias of V, that bias is going to be the expected value of V minus sigma squared. We just said the expected value of the V was n minus 1 over sigma squared. And if we do the difference between those two, you'll get a minus sigma squared over n. So that's how we calculate bias. So one of the things that we would like, it's not always possible, and sometimes it's not always necessary, but one of the things we would like to have for our quality that we would like our estimators to have is that it is unbiased. That when we do, on average, if we do this over and over and over and over again, we would like our expected value to come out to be the actual value of the parameter of the population parameter. So let's do a couple of examples here where we can, let's do an example here where we can try to figure out what do we have to use for a constant to get an unbiased estimator. So let's look at this example problem here. We've got a random variable. It's a binomial random variable. And instead of using an n, they're using an m here. So they're letting the q hat be our x over m. We already know from previous work, for what we've done before, we know that the q hat is an unbiased estimator of q. We can check that pretty quickly. If you do your expected value of your q hat, that's going to be your expected value of x over m. We know that constants pull out of your expected value. And they tell us in the problem that x is binomial. And we know that the mean for a binomial distribution is trials times probability of success. And if we simplify, we get q in this case. So again, this is the idea for being unbiased. To be unbiased, you need to have an expected value that turns out to be the actual value of the population parameter. All right, so the problem now asks, I just went through that to verify that we really did have an unbiased estimator here, that we weren't dealing with a biased one. All right, so from this, we want to find an unbiased estimator of q times 1 minus q. All right, so let's just look at our natural inclination, or at least my natural inclination here, would be to try to figure out how to do this in terms of the q hat. Okay, so what if we just plugged in the q hat for the q? Right? We're using q hat to estimate q, so why not use q hat to estimate q hat times 1 minus q hat? Seems to make sense to me. All right, so if we wanted to do this, we would need to distribute. And then I've got expected value of q hat minus the q hat squared. We know that we can split up expected value over this difference. Now, we already know what expected value of q hat is. We know that's q, without a doubt. We just showed that up in the previous line. Well, I guess it was 3 lines ago, but same idea. All right, so let's see if we can figure out the expected value of q hat squared. Now, I know that I can't just pull out the squared. However, I do know that this will be equal to the variance of q hat plus the expected value of q hat quantity squared. Remember that our variance, one of the ways to calculate variance, I'll write this up at the top here, one of the ways to calculate variance of a variable, of course, is to do expected value of x squared minus expected value of x quantity squared. So all I did here was just add over the expected value of x to the left-hand side. Pardon me. So let's see if we can figure out these values here. So I still have the q out in front. My q hat is x over m. And I already know what expected value of q hat is. We already determined that was q. So this will be q squared here. We can, what are you doing? Stop doing that. We can pop out this m out of the variance. But when we pop out constants out of the variance, of course, we square them. So we get 1 over m squared, variance of x, and then plus q squared here. Variance of x, well, we already said that the that x is a binomial random variable. So we know how to calculate its variance. So the variance for that is m times q times 1 minus q. And notice that one of our m's will cancel there. Now let's move some things around here just so that we get, basically we're trying to simplify some stuff here. So I have a q out in front, and I've got a minus q squared there. And then we've got a minus 1 over m q times 1 minus q. Pardon me. This term in front is q times 1 minus q. If I factor out a q out of those first two terms, I get a q times 1 minus q. So I'm going to factor that out. We'll be left with a 1 in the first part and a 1 over m in the second part. So we can write this as q times 1 over q times m minus 1 over m. Oops, not minus. All right. That was a lot of work to get there, but let's talk about what we have. We have, remember that we're trying to find an unbiased estimator for our q times 1 minus q. We tried q hat times 1 minus q hat because we already had an estimator for q. Notice that we have the q times the 1 minus q. That's a good thing to pop out because that's what we're trying to estimate according to the problem. However, we've got some bias. We've got that m minus 1 over m behind it, right? So, to get rid of that bias, we can do m over m minus 1 times the q hat 1 minus q hat. If I put that m over m minus 1 out in front and then do the expected value, it'll cancel out the m minus 1 over m. So if I do m over m minus 1 times that expression, this is an unbiased estimator. For q times 1 minus q. Questions on that at all? So if I do the expected value, if I put this m over m minus 1 piece in here, multiplying that q hat times 1 minus, I could just move out in front because it's a constant and it'll cancel the m minus 1 over m. Other questions on that one? Let's do another one like this one. I don't have it on the note paper, but I want to add it in here just to kind of reinforce the same idea. So let me do this off to the side. Let's say we have, you know what? I'm going to kill a window. I've got some lag going on my own computer, so I'm going to kill a window, see if maybe it's get rid of some of the lag. Let's say X is a single observation from a uniform distribution on 0 theta. So then 2x is an unbiased estimator for theta. And the reason for this is because if we do the expected value of 2x, well, that's 2 times the expected value of x. Even though x is just a single observation from the uniform distribution, well, if we do that single observation and then do another single observation, do another single observation, do that over and over and over again, we essentially have that uniform random variable. So we might as well treat x as uniform on 0 theta, which means its expected value is theta over 2. It's halfway in between, and we really do get theta. So that's why our 2x is an unbiased estimator for theta. Let's see if we can figure out the... Sorry, go ahead. Does somebody have a question? I thought I heard something. Yeah. Okay. Well, I'm glad I'm not... Well, I hear voices all the time, but I really did think somebody had a question. All right. So let's see if we want... let's calculate the bias in 2x squared. 2x quantity squared as an estimator for theta squared. So much like what we just talked about in the previous example, we had an unbiased estimator for Q, so we tried to use that to estimate Q times 1 minus Q, and some bias popped up. So in this example, we have an unbiased estimator for theta. Let's try to use the same estimator to estimate theta squared and see if any bias pops up. So remember again that the bias in an estimator is the expected value of that estimator minus what you're trying to estimate. So in this case, we're trying to estimate theta squared. So we want to know what the difference is between that theta squared and the expected value of what we're trying to use to estimate it. Pardon me. So, probably the easiest way to do this one is to do it like we attacked the previous one. We had to do that expected value of q squared. For the expected value of q squared, we had to use pardon me, the formula for the variance of q pardon me. We had to use the the variance formula to get an expression for the expected value of x squared. So for this one, we'll have the variance of 2x squared plus the expected value of 2x quantity squared, and then we'll have the minus the sigma squared, or excuse me, the theta squared on the end. We're just using that same formula for the variance, just rewritten. Something's going on crazy with my voice. Oh, goodness. Sorry about that. All right. What's that? Oh, yeah. Go ahead. Sure. Oh, it's not. It should just be 2x. Thank you. Thank you. It should just be a 2x. Thank you. I needed that part. I was thinking I'm going to square the 2 here in a second anyway. Remember that it's... remember that our variance formula just for x is expected value of x squared minus expected value of x quantity squared. And we're replacing the x with 2x. Okay. So now that I have variance of 2x, I can pop the 2 out front, but when I pop the 2 out front, I got to square it. I know that expected value of 2x is just theta, so I get plus theta squared. And then I've got minus theta squared still on the end. So those two pieces are going to go away. And then for the last bit here, I need variance of x. Well, we can get the variance of x just like we were talking about getting the mean for x, the expected value for x a little bit ago. X is uniform. And we have a formula for computing the variance for a uniform distribution. When it's uniform on AB, remember the formula is b minus a quantity squared all over 12. So in this case, we just get theta squared over 12. And that simplifies to theta squared over 3. So that gives us our bias. Any questions on that at all? The bias that's in the 2x quantity squared. Basically, on average, it's how far it's off. And the way we have it defined, it's actually going to be too high because it's a positive value. Notice that we have it as expected value of the estimator minus the expected, or minus what the parameter is. So if it's positive, on average, the estimate will be too high. because it's a positive value in this case. Correct. Yep, exactly right. On average, it'll be above what we expect, what we will, what the actual value is. That's exactly right. Correct. Yep. Yeah. And as a matter of fact, I mean, if you know the bias, then you know the expected value. So we know now that the expected value of the 2x squared must be the theta squared that you're trying to estimate plus the bias that's in it. So you'd have 4 theta squared over 3. So if you, so go ahead. Yeah. Yep. Sorry. So if we now know, since we know the bias and we know what it's trying to estimate, we know the expected value. So the expected value of our 2x squared here is just your theta squared, what you're estimating, plus the bias in the estimator, and that adds up to 4/3 sigma theta squared. So if you want to make it an unbiased estimator, you would just need to multiply by the 3/4, like we did in that previous example when we multiplied by the m over m minus 1. Did it come through that time? Oh, gotcha. Did that make sense that time? Okay, cool. All right, any other questions on that one? All right, where am I? There I am. Okay, let's see if we can do another one with an unbiased, try to find another unbiased estimator here. So, this one asks us, we have independent random variables here, x and y, and they want to try to find an unbiased estimator for theta to the negative 1. And then it asks us what the value of k has to be. So, x and y are both distributed the same way. So the first thing we're going to want to do, if we want to try to figure out an unbiased estimator for anything, the first thing we want to do is figure out an expected value of the particular variable that we're using to trying to estimate something. So the first thing we want to do is try to find the expected value of x. That's going to be step 1 here. Okay. All right, so when we do expected value of x, we want to integrate over the support. So we're going to do the integral from 0 to 1 over theta. And then we'll take x times the PDF, so 2x theta squared. So we're just integrating 2x squared, so that gives us 2/3. There goes. 2/3 x cubed theta squared. Theta is just a constant as far as the x is concerned. Go from 0 to 1 over theta, and what does this simplify to? We get what? 2 over 3 theta? Erase. There it goes. All right. So now going over to the expression they're asking us to do, they want to construct an unbiased estimator for theta to the negative 1. So I want to figure out what is the expected value of that k times x plus 2y. Well, again, we can pop the k out front, and we can distribute the expected value over the sum, and in that second one I can pull the 2 out in front as well. X and Y have the same distribution, and we just computed what the expected value is for each, well, what X is and when the Y has the same distribution. So we've already calculated the expected value of X and the expected value of Y. Both of those are going to be 2 over 3 theta. So what do we get? We get 2 over theta. Because I'm pretty sure we get 4 over 3 theta and 2 over 3 theta, so we get 6 over 3 theta, which reduces to 2 over theta. What do we want this to turn out to be? Well, remember, we're trying to get an unbiased estimator for 1 over theta. So we want this to equal 1 over theta, because the problem is asking us to find an unbiased estimator for 1 over theta. Well, if that's the case, then we better get k to be 1/2 in this case. So again, just basically to recap, pardon me, just to recap here, the first thing we did was figured out what the expected value was for one of the variables before I even tried to get into the expected value for both of them. Did that first, and then it's asking for an unbiased estimator using that particular computation. So I went through and figured out what the expected value was for that computation. That was where we got the k times 2 over theta. We want it to be unbiased, so we want that to equal 1 over theta. That's what it would mean to be unbiased, that the expected value turns out to be the parameter we want. And then I just solve for k. Yeah, that's exactly what it's doing. It's trying to make that, in this case, you've got a statistic that you're computing. Basically, you can think of X and Y as a random sample of 2. So you're trying to make that random sample of 2, whatever statistic you're using to compute, you want to make that that statistic be an unbiased statistic. So you are using the k to scale it so that it's unbiased. That's exactly right. You got the idea. Yeah. Well, if I did, I would have needed to change the PDF variable to a y as well. Because I get the same thing. Yep. Other questions at all on that? All right, let's do one more here. So we've got a random variable with mean 2, and it tells us that S and T are unbiased estimators of the second and third moments about the origin. So all that means is that if I do the expected value of x squared, that's equal to S, and the expected value of x cubed is T. So, goodness gracious, sorry. The moment about the origin just means that you're not subtracting anything from the x to start with. So, second moment is just expected value of x squared. Third moment is expected value of x cubed. This one wants an unbiased estimator of the third moment about its mean. Well, we're told that the mean is 2, so we're asked to figure out what is the expected value of x minus 2 cubed. Pardon me. So we want a statistic that ends up equaling this. So this is a lot of words for something that's not all that hard in this particular case, because All this means is the third moment about its mean means I'm just going to do x minus the mean and cube it. We're going to do some algebra here. X cubed minus 6x squared plus 12x minus 8. When we cube that, split everything up. So just breaking it up and pulling out the constants where we can. And now we know either numbers or letters for each of these. Expected value of x cubed is t. Expected value of x squared is s. Expected value of x is 2, because they tell us the mean is 2. And expected value of a constant is just the constant. What is that, 16? So you get t minus 6s plus 16. So like I said, this problem had a lot of words to it, but I just wanted you to play around with the idea of getting the estimators. So if s and t are unbiased estimators of the second and third moments, that's where we got the equations over here on the left. Now notice what the form of the equations look like. Expected value of x squared equals s. That's what it means to be an unbiased estimator. That when you do the expected value, you get the whatever the estimator is that you're trying to find. So that's all it wanted us to do, is find a formula for expected value of the x minus 2 cubed in terms of s and t. That was all it asked us for. So basically, this was a problem that I wanted to put on here just to go back through not only the definitions for unbiased, but the idea of the second and the third moments. Questions on that one at all? All right. Well, we'll do more of this next time. Same sheet, like I said. May even spend a little bit on Monday on it as well. Could everybody hear me okay today? Was it better today? Good. Yeah. Well, yeah. There's also some lag on me writing actually on my screen. So part of this might just be that something funky is running in the background too. So, but anyway, I'm glad I was able to hear me today. I'm glad I was actually able to talk to you today instead of talking to myself and recording. So that made me happy. Yeah, it was not fun for me either. So, anyway, oh, good. Yeah, well, I meant it too. So, but anyway, it was good to hear you all today. So, thank you for coming back. All right, yes. Oh, thank you. Yeah, you're welcome. All right, everybody. Well, we'll talk to you on Friday then. Yeah. It's in chapter 10. There's not really a section. The way our book does it is kind of weird. It's very, very I find it very, very choppy. I found a PDF of another book, and I'm going to send you the link to it and tell you the chapters that make sense in there. I'm trying to go along with it a little bit more because I think the format, the way it was presented in this other book, isn't fantastic necessarily, but at least it's a little bit more coherent to me than the way that our book does it. Our book seems to do it a lot more segmented, so I will get that sent out today. Yep. Yeah. Yeah, it's gonna be Friday. Yep. Well, because because your homework's due today, and I want to get an opportunity to get it graded and back to you in case there's something that you're doing wrong. So I want to make sure you have enough time to fix it if there was something that you were doing wrong in the homework. Yep, anything else? Okay. Which one was it? I'm sorry. So I think you should just be able to run the t-test on the because you're just doing the difference of the means for that one. Yep. So that's all I want you to do on that one. Okay. Anything else? Or are we good? Okay. We're good. All right. Well, I'll talk to you all later. Have a good one. Yep. Bye bye.